Hey, so my name is Kaleigh, and I am going to talk about simulating nonlinear waves on vortex winds and ideal fluids, which is research that I've been working on with Dr. Sketchdown. And so kind of the motivation between this is that we have nonlinear waves on vortex winds, and these are really fundamental for understanding energy transfer and quantum fluids or low temperature fluid dynamics. And it's also really important to understand how things like quantum turbulence relax in nature with this absence of viscosity that we usually see in classical fluids. So there's no opposing to shearing in this case. And so that changes how these structures relax. And so one of the biggest challenges of this is being able to build these curves and understanding the mathematical equations to build these curves. And so that's something that we've been kind of working on in order to be able to simulate and then further understand. And so these can be approached in multiple ways. The first way that we approached it was using the circular functions. And that's can be seen, the image that we got can be seen down here in this bottom corner. And the circular functions are great, but they're also limiting to how much we can do with it. And so then we kind of moved towards the work of Hashimoto, where he has worked on this, building the soliton, but he's only built it on an infinite line, but he uses the hyperbolic trig functions, and it allows us to localize different parts of the curve. And so we've kind of worked with that and built a little bit, and we put it on a track, but when you do that piecewise, it can kind of create custom at those endpoints, which can be difficult in simulations. And so ultimately we use the Jacobi elliptic functions, which gives us that ability to localize like we have in Hashimoto's, which also gives us that circular track like we see in our circular functions. And so that gives us both properties. It's a little bit easier to work with. In addition to that, it's important to understand the curve geometry. And so two of the biggest properties of that is the torsion and curvature. So the curvature is how much something wants to be a circle and not a straight line. And our torsion is how much something wants to like bend out of a 2D plane. And so we kind of can graph that and look at that to try to understand. And using those, we can also approach this equation using the Frenet-Soré equations, which gives us a system of differential equations to be able to find the like vector field at each of our points using a fixed curvature and torsion, which can also help insight. And so getting these, we would give our initial conditions of our simulation, our starting points, and then we can simulate these through time and see how the curve evolves through time. And while it evolves through time, we get this induced velocity field, and we can see that can be related as it goes into our binomial direction or travels in our binomial direction, which is represented by green arrows. And that's going to be proportional to the magnitude of our curvature. Yeah, thank you so much. If you have any questions, feel free to ask.